Hey everyone, buckle up because today we're diving headfirst into the world of metal organic frameworks.
MOFs. Yeah, they're really changing how we think about materials.
They're like the Legos of chemistry, right? Building blocks for the future.
Exactly. Except these Legos can capture and store energy, clean up pollution, and so much more. It's all thanks to some really cool chemistry.
You're our guide into this amazing world today. We're taking a deep dive into a 2013 Science article that really lays out just how groundbreaking MOFs are.
It's a classic for a reason. A lot of the concepts we're still building on today.
So, for those hearing about MOFs for the first time, what's the elevator pitch?
Imagine snapping together metal ions and organic molecules, kind of like tiny building blocks.
Okay, so we're talking nanoscale construction here.
Right, but the structures they form are anything but basic. You get these repeating, porous structures, picture a sponge, but with teeny tiny, precisely engineered holes.
A super sponge. I like it. But what makes that special?
It's all about surface area. We're talking huge GE surface area packed into a tiny amount of material.
How huge are we talking?
How about a single gram of some MOFs can have the surface area of a football field?
Whoa, wait. A football field is something I can hold in my hand. That's insane. No wonder people are excited about these things.
And that incredible surface area is what gives MOFs their superpowers. We can store tons of gas, filter out specific molecules, even build tiny chemical factories at the molecular level.
Okay, now you've really got my attention. But before we get to all that, back up for a sec. You said there are over 20,000 different types of MOFs.
Yeah, and counting. That's because this technique we use, what we call reticular synthesis, lets us create strong bonds between the metal ions and organic molecules.
So it's not just about making any old structure, it's about making ones that last.
Exactly. Strong bonds means stable frameworks. And with so many building blocks to choose from, we can fine-tune those frameworks for an amazing range of applications. It's like having a chemistry set with infinite possibilities.
A chemistry set that can change the world. All right, we've got these incredibly versatile, porous materials. Now let's talk about what they can do. Okay, MOFs sound pretty amazing so far, but let's talk about their superpowers. You mentioned storing huge amounts of gas. That's got to be huge for things like energy, right?
Absolutely. Think about storing enough hydrogen to drive a car across a continent, or maybe even capturing enough carbon dioxide to make a dent in climate change.
Wow. Okay, I'm definitely interested, but how do MOFs actually make that happen?
It goes back to that massive surface area we were talking about. It's like having tons of tiny storage compartments all ready and waiting to hold those gas molecules.
So like a gas trap, but on a miniature scale.
Yeah, exactly. And we can even customize these traps by designing MOFs with specific pore sizes to target particular gases. Take MOF 177, for example. It's incredible for storing hydrogen.
MOF 177, catchy name.
Yeah.
So is this thing setting records?
It actually holds the record for the highest surface area of anaway porous material.
Okay, I'm trying to picture this a tiny MOF holding all that hydrogen. But how do we get the hydrogen back OUT when we need it?
Oh, that's part of the beauty of MOFs. We can design them to release the gas under certain conditions, a change in temperature or pressure, perhaps. It's like having a gas tank that we can control at the molecular level.
That's really incredible. And you said earlier that we can actually adjust the size of MOFs, too. That sounds like something straight out of a science fiction movie.
It does, but it's 100% real. Picture this. We can make a MOF 17 times larger without changing its fundamental structure. It's what researchers have done with HKUST1.
Wait, so it's like inflating a balloon, but instead of air, it's this complex material with pores and channels.
You've got it. That flexibility opens up even more potential for storing and releasing gases exactly when we need them.
This is amazing stuff.
Okay.
So huge storage, adjustable size. What other tricks do MOFs have up their sleeve?
Well, we can tweak their properties even further with something called post-synthetic modification, or PSM.
PSM. Okay, you're losing me a little bit.
Remember the Lego analogy? Imagine building your MOF structure and then deciding to add some extra features. With PSM, we can swap out individual Lego pieces, those organic molecules, after the MOF is already built.
So we can give it like a chemical upgrade, change its abilities.
Exactly. We can add specific groups of chemicals to give a MOF new abilities. For example, we can create what are essentially tiny reaction chambers, catalytic sites that speed up chemical reactions.
Hold on, so MOFs aren't just for storage. We're talking tiny chemical factories now.
Precisely. And these factories can be designed to make all sorts of useful products, clean energy, maybe even life-saving medicines.
So we've got MOFs storing tons of gas, changing sizes like something out of science fiction, and even acting as these tiny chemical factories barely keeping up.
Mm-hmm.
But how do we actually use these things? Like, what real-world problems can they solve?
Well, let's take gas separation. MOFs can act like super efficient filters, separating different gases at a molecular level.
Okay, like way more precise than any filter I've ever seen. What's that mean in practice?
We could use them to capture harmful pollutants from the air, for example.
Oh, wow. Cleaning up pollution, that's a big one.
Exactly. Or we could purify natural gas, making it even cleaner and more efficient.
So it's not just about storing the gas, it's about choosing the right one. I bet all sorts of industries would be interested in that.
Absolutely. And remember how we talked about post-synthetic modification, or PSM, those chemical upgrades we can make to MOFs? Well, that opens up a whole other world of possibilities beyond gas storage and separation.
Right, the chemical upgrades. So we can make them do even more, like...
We could potentially use them for targeted drug delivery.
Hold on. We're talking about using MOFs to deliver medicine in the body, like right where it's needed.
You got it. Imagine designing an MOF with pores that are just the right size and shape to hold a specific drug molecule. Once inside the body, the MOF acts like a delivery truck, releasing the drug only when it reaches the target, like a tumor, for example.
That's incredible. We're talking about revolutionizing how we treat diseases.
Precisely. And because it delivers the drug so precisely, it could mean fewer side effects, too.
That's a game changer. Okay, from super sponges to tiny factories to drug delivery systems, is there anything MOFs can't do?
Well, we're constantly discovering new possibilities. There's also their potential as highly sensitive sensors, for instance. Imagine an MOF that changes color in the presence of a specific pollutant, acting as an early warning system for environmental hazards.
So they're like tiny environmental watchdogs, too. It's official. MOFs are the superheroes of material science. You mentioned something earlier. I want to circle back to MTV MOFs. It sounds kind of like a TV channel, but knowing this field is probably something even cooler. What are they all about?
You're right. Definitely not a TV channel. Remember how we can use PSM to give MOFs multiple functionalities? Well, MTV MOFs or multivariate MOFs take that to a whole new level. Instead of adding functions after the fact, we design them with multiple components from the start, each with its own specific tasks.
Okay, so it's like building in those extra features from the ground up. Give me a visual. What could we use that for?
Picture a MOF that not only stores hydrogen, but also acts as a catalyst to help release that energy right when and where you need it.
Wow, so it's like a self-contained energy system at the molecular level. We're talking about engineering materials with the same kind of complexity and efficiency as nature itself.
Exactly. And this is just the beginning. The more we explore MOFs, the more we realize their potential to address some of the world's biggest challenges. The future of material science is here, and it's looking pretty exciting.
This deep dive has been mind-blowing. We've gone from basic building blocks to mind-boggling applications, all thanks to the incredible world of MOFs.
And the most amazing thing is that we've really only just scratched the surface. Who knows what incredible discoveries and applications await us?
If you're as fascinated by the potential of MOFs as we are, I highly recommend checking out the full article, The Chemistry and Applications of Metal Organic Frameworks. It's a real eye-opener. Until next time, keep those imaginations firing because the future of material science is full of possibilities.